Well, folks, we are back again. Welcome to our third video lesson on waves. Today we're going to look at what happens when waves encounter boundaries. So this is very similar to the way I like to kind of introduce this is if you think of like an object. Like if I were to take a ball and throw it at a wall, anytime an object encounters a boundary or a change in the medium. So for example, ball bouncing off a wall would be going from air to a solid object like a wall. An object that encounters a change in medium is going to hit that new boundary or whatever it might be and is going to bounce back. So there are specific things that occur when a wave encounters a change in medium. There are three main details, what are called reflection, refraction, and diffraction. So in this one, we're going to look at the case of reflection when a wave encounters a boundary and is going to bounce back. And we also kind of talk about what happens when a wave is transmitted into a new medium. So a couple of vocabulary words that we have here. We have the incident wave. So that is going to be the crest or the trough or a complete wave possibly or continuous wave. These are the things that we are creating and what is moving towards the boundary. So the incident wave is going to be the wave phase or pulse before it encounters the boundary. It is then going to encounter the boundary, which you can see here. That boundary could be either a fixed end, a free end, maybe it's going from one medium to the next, but when it encounters a boundary, part of that wave is going to be reflected back into the original medium, and that's going to be obviously our reflected pulse. And then potentially if instead of going to like a fixed boundary like we have there, let's say that we have a wave that's encountering maybe a change in medium where it could actually pass through, that if there are any part of the wave, I should say, that's transferred through, we're going to call that the transmitted wave. Now what we're going to do is we're going to look at in this lesson the specific types of boundaries you can have and what is going to happen to the wave itself. So we're going to talk about, and I'm going to discuss kind of the word phase. And phase is referring to whether, especially for a transverse wave, whether we are looking at a crest or a trough. If this was a longitudinal wave, we'd be talking about compressions or potentially rarefactions. Okay, so it could occur for both types of waves. Easier for us to see, obviously, with a transverse wave. So let's get it. Okay, so what we're going to look at first is what occurs when a wave encounters a fixed end. So you'll notice on the right side here, this is a simulation you guys did. There's a clamp there that is used to fix that end so that it's not moving. So what I did is I created a pulse already. You'll see that here I have a crest, and that is the incident wave. So that crest is going to move towards that clamp, which is locked in place. And our goal is to try and understand what happens to the phase of this wave as it's reflected back into the medium. So as it hits the wave, you'll notice, boom, it reflects back. And notice that in this is kind of neat, and I can let it go because both ends are technically fixed ends. I have the generator on the left side and the clamp on the right side, both are fixed. You notice that every time it hits a fixed end, that wave phase is being inverted. It goes from crest to trough, and then from trough to crest. So that is what we are going to say for a fixed end reflection. Is anytime we have a fixed end, that is where the boundary is not free to move. This could occur when you have, for example, like the ball hitting the wall for a physical object. For a wave, it would be the same thing. Let's say it's a sound wave. Let's say that I yell and I'm standing next to a building, that when that sound wave hits the wall, that would be a fixed end. Or if I were to send, like you're seeing a wave on a string where that end is not able to move, that again is a fixed end. Now, anytime we have a fixed end, what I want you guys to know is that our incident pulse and our reflected pulse are always going to be inverted in phase. So if, for example, I have a crest, when it hits that fixed end, it's going to reflect back and become a trough. Now, the reason why that is that when it approaches this fixed end, that end cannot move. So why the wave becomes inverted is a combination of all three of Newton's three laws of motion. The first law stating that an object at rest wants to stay at rest. It has to deal with a property called inertia. That if we face a fixed end, we want to think about that object as having more inertia to it, meaning that when that wave encounters this fixed end, this end does not want to move. Therefore, it's going to do everything it can to not move. Now, the reason why it might not want to move has to deal with Newton's second law that states that the movement or the acceleration is a ratio of the force to the mass. So if we have a fixed end, think of it as having a greater mass, which means that it's not going to accelerate, which means it's not going to move. And why does that become inverted is because of Newton's third law, which was our action and reaction pair, that as the wave hits this fixed end, that the wave wants to, because it's a crest, wants to pull it up. But since this thing is more massive, more dense, it's going to pull it down, and that's why it becomes an inverted phase. And the same thing is that if this was a trough, if it hits this fixed end, again, it wants to pull it down, but this fixed end is going to pull it back up, and that's going to cause it to become a crest. So all this has to kind of deal with Newton's 3 laws of motion, just looking at waves. But anytime it encounters a fixed end, we're going to see that that phase is going to be inverted. All right, so next one is when we look at a free end. So you'll see here, again, that pulse. I have another pulse created. Again, it's a crest. We are looking at a loose end, which is the same thing as saying a free end. Now, obviously, this is different, that end on the right side is not clamped down. So I have here a crest. This is my incident wave that's heading towards that free end. In this case, when it hits that free end, you'll know that all of a sudden it bounces back and in the same phase. And you'll see here, again, I now have a fixed end on the left side, a free end on the right side. So you'll see anytime it hits that free end, it's going to reflect back the same phase. When it hits the fixed end, it's going to bounce back in the opposite phase. Okay, so for a free end here, we're seeing that it reflects back in the same phase. So free end boundary is one that is free to move. We can also think of it as a less dense boundary. So this is kind of the opposite of what I just talked about for a fixed end. A free end is able to move. So that when we look at Newton's 3 laws, this free end would have less inertia, meaning it is more capable of moving than if it had more inertia, and that is because it'll have maybe be a less massive or less dense medium, and that will then cause it to accelerate faster. And then Newton's third law, because it's a smaller object, if it's being pulled up, in this case it is actually going to move up, which is going to send back the same phase, and same thing if it was being pulled down. So as this incident wave comes in, it's going to pull this boundary up, and because that boundary is less dense, that boundary is going to move up, and then that boundary is going to come back down, and that is going to be why it sends back a crest. So for a free end, you are going to have the same phase being reflected back into the medium. All right, and this is the last one. This is the fun one. Tough one as well, folks, is what happens when there's no end. Let's say I create a wave pulse, and ho! So understand that sometimes if there's no end there, that wave will keep going through, okay? And that's just going to keep passing through. That is a transmitted wave. I do want to talk about then what happens when a wave does actually pass through into a medium. So understand that if the medium stays the same, the wave will travel the same speed throughout that medium, and it will not encounter any sort of changes unless there's any sort of internal friction within the medium. But as we talked about, waves will always travel at a constant speed related to their frequency and their wavelength. But what happens when we do have a wave that passes into a new boundary? So this is what we're going to look at called transmission. It's also another property of waves called refraction, but we're going to get into a little bit more of that detail later on. But when a wave encounters a boundary and is able to move through, like here I have 2 strings, the red string and the blue string, where the red string, just by looking at it, is less dense, it's less massive, and the blue string is more dense or more massive, and the boundary is right here, okay? So we have 2 things that could go on when we have a wave being transmitted through that boundary into the new medium. Okay, it could go from, for example, a less dense medium first to a more dense medium. So think of me having an incident wave or incident pulse as a crest, and it's going to encounter this boundary right here. So this boundary, because we're going from less dense to more dense, you can treat this as encountering a fixed boundary, okay? This goes back to the whole Newton's laws I talked about before, that when that incident wave hits that fixed end, what we're going to see is, because this is more massive, it's going to have more inertia, it's going to not want to move, and since this is going to try and pull it upwards and it doesn't want to move, it's going to pull it back down. And therefore the reflected wave is going to be a trough. However, waves are energy. So what ends up happening in a real life situation is that anytime a wave encounters a boundary, and this is where it's different than an object, is that energy will be passed through. When I throw a ball at a wall, the ball does not partly go into the wall and part of it bounce back. But waves being energy, that is actually a possibility. So what will happen is anytime a wave encounters a boundary where it is able to pass through or transmit itself, that part of that energy will actually transmit through into the more dense medium. And you'll notice that if it was a crest to start, you'll see that it's still a crest as it goes on. Now, if you compare this incident wave to the transmitted wave, you'll notice here what I have is, in this case, you have a larger wavelength, and here you have a smaller wavelength. So you'll notice that as it travels into a more dense medium, that the speed is going to be affected. So in this case, if the wavelength is decreasing, that means it's going to decrease its speed overall as it goes into a more dense medium. So treat that as like a fixed end. Part of it is reflected, and part of it is going to transmit or pass through. Same thing can be said in reverse then, is that when we have an incident wave going from a more dense medium to a less dense medium, you can treat that boundary condition as being a free end. So free end means is that it is going to be going into a less dense medium. So this less dense medium is going to be it's going to be free to move. It's not going to have as much inertia. So this incident pulse that's being shown here as a crest, as it hits that boundary condition, it's going to be reflected back as a crest. Because again, if this is able to move, it's going to be pulled upward and it's going to move upward. Okay, so that's Newton's third law, which in that reflected wave would be a crest. And you'll notice here then that the transmitted wave is still a crest, but what you're going to see here is that the wavelength goes from being a smaller wavelength and here going to being a larger wavelength because it's being able to move faster in a less dense medium. Also, one other thing to recognize here is that as we go into a wave being transmitted through, another piece of this is going to be the amplitude. Okay? Energy of a wave is represented by its amplitude. So if some of the energy is being passed through, you'll see that here the amplitude is much smaller than the original amplitude. Here this amplitude is also smaller than that amplitude, but the idea is this, is that if I were to add the amplitudes of our two waves, the reflected and the transmitted, so if I were to do the amplitude plus the amplitude, it should equal the incident amplitude. That energy has to be conserved, that some of the energy that's passing through plus the energy that's reflected back should equal the amount of energy we have in the original sense. So this was looking at, again, what happens when waves encounter a boundary, whether it's fixed, free, or if we have a transmitted wave going into a new medium. If you guys got any questions, jot those things down. Otherwise, peace out.